Hi, everybody. We're online. There we go. There's everybody. Isaac, Ryan, Zach, Julia, Sam, Lena, Aaron, and Kevin.
Hello.
You are the motley crew. Shannon, you're not here. I know you've been taking notes from home. We miss you in class, but the rest of you guys are awesome. Isaac, you're supposed to smile. I'm awesome. Do you guys have any questions? Are you ready for the end of the semester? How's your other classes gone?
Pretty well.
Okay, good. You guys taking classes this summer?
I am. I just signed up last night.
Julia, are you taking classes this summer?
Yeah, I'm taking 2 classes.
Online again?
Yes. And they're 5 weeks, so I feel like it's going to go really fast.
Yes, it will go really fast. Why aren't we back in school? Somebody tell me why. Why aren't we back in classes? Yeah, I'd like to know why. Okay, so what were we talking about the last day on Tuesday? What was the last thing we talked about? Because we went kind of fast, didn't we?
We talked at the end about baroclinity, with like short waves are baroclinic and then long waves are barotropic.
Oh, right. Okay. So what I want to talk about, I think I'm going to just set it up this way. Okay, so we've already kind of done this, but I'm going to do it like this. Oops, I want that. I want a line. I want this. No. Well, this is what I want. Water, land. Okay, and we already said that we had initially, we have this. I'm going to do it this way. And we'll call this P minus delta P minus 2 delta P. What are these lines?
Isobars?
No, they're not isobars. Why aren't they isobars?
Oh, because they're vertical?
Yeah, this is a vertical surface, right? Isobars are drawn on horizontal maps. So this is a horizontal. So what are these lines then?
Isotax?
No.
Isobaric planes.
That's the cross section of an isobaric plane or an isobaric surface, right? So you have to think of these as actually being kind of a, there's a surface here. This, right? That's the plane. But what we're saying is that initially, everything's the same. So we have the same amount of air above me here when I'm just a person walking on land, or when I'm given miraculous powers and walking on water. I have the same amount of air above me, okay? But then the sun comes out. And when the sun comes out, it's going to heat differential, right? So there is, basically in here, there is going to be differential heating. So let's just think about all these things. Differential heating. Which means there's a temperature gradient, right? And it's going to be warm here. Now, initially, was there wind? Before any of this happened, was there wind?
No.
What is the pressure, let's say, right here?
P minus 2 delta P.
What's the pressure right here?
P minus 2 delta P.
Is there a pressure gradient? From here to here, is there any difference in pressure? The answer is no. If there's no pressure gradient force, then there's no wind. So this thing initially has no wind. But when the sun comes up and heats these things, do you agree that the right side is going to have more warmth above the ground than over here where it's cooler? What will that do to our isobaric surfaces?
Would slant them.
First thing is it's going to slant them like this. Okay, so this is P minus 2 delta P like it was before. What is this diagram expressing or illustrating? What is this what concept is this expressing?
Yes.
Aaron?
E. A. She says it's sea breeze.
Okay, it is going to be a sea breeze, but Aaron, what I'm asking is the fact that these isobaric surfaces are farther apart because it's warmer tells me what?
No.
Anybody? What do we got?
That's right.
What is this demonstrating?
Can't remember the saying, but it's like thicker the warmer, thinner the cooler.
What is that called? Yeah, you need to know the name. But you're right.
Is that hypsometric, the thickness relation?
Hypsometric. What is the hypsometric in official? Now, the thicker the warmer, the thinner the colder is what it is. But what is it in official terms? Like the official definition of the hypsometric? Do you have it written down? Lena, do you have that?
I just have the thicker the warmer stuff.
That's what it is. So the thickness is the vertical distance, delta Z, between two isobaric surfaces is directly proportional to the average temperature of that layer. That's why I say the thicker the warmer, the thinner the colder. But that's the hypsometric. It basically says delta Z is proportional to the average temperature. Okay. This equation, by the way, derived from, remember we talked about the ideal gas law, which relates pressures and temperature and density and the hydrostatic. What is the hydrostatic equation? What's the hydrostatic?
It's -1 over rho times change in, or times the pressure gradient force is equal to gravity times the vertical height gradient or height gradient.
Well, I'm just going to make it simpler right there, right? That's what it is. This is the pressure gradient, vertical. But this, the left side is, when you have it 1 over rho, it's the pressure gradient force. But when I derive these two, ideal gas law, hydrostatic, by the way, you have to use calculus. This is something we do in our intermediate meteorology class. If you ever want to test yourself in higher level math, that's what you will do. But we're only going to talk about it. And that's what we're saying. Now, do you agree what that establishes is the wind aloft starts blowing from the right to the left because the pressure at some height is higher there than it is over here. Now, do you understand that there is convergence of air over here, convergence, and divergence of air over here? And that means I'm removing air from the column. So what will the pressure do at the ground?
Lower.
It'll be lower. So I get low pressure on the ground, but air is converging over here, so the pressure on the surface will be higher. And then we just kind of figure out that the winds, mass continuity says convergence leads to sinking air. It's going to come across and it's going to go up like this. But we've done this before. This is, like Aaron, you said, this is the sea breeze circulation. But there's something that we didn't do, and that is that the pressure here is going to decrease. So this isobaric surface is going to come down like this. So that if this is isobaric surface with a pressure of P, what is the pressure there? More than P, right? And what's the pressure here? Less than P. Now watch. I walk this way. Tell me when the pressure rises and gets to P. Okay?
There.
Okay? So right there, the pressure is P. Do you understand that this is a, this is a surface that goes into the board? So what is drawn on the ground is this. I get an isobar. So this is where I am over here. We'll call this letter A. And we'll call this letter B. And I get an isobar. Because what's the pressure? What's the pressure at A? Less than P. And the pressure at B is greater than P. Do you agree with this? In other words, if I take a plane, right? Here's a plane, it's a little surface, but when I hold it sideways, you don't know what it is, it's just a line. And I intersect it with another plane, piece of paper. That intersection, what I would draw on that is just a line. So what is an isobar really? An isobar is the intersection of an isobaric plane and a horizontal plane. Write that down. An isobar is the intersection of an isobaric plane and a horizontal surface. Now, review. Do you agree that this isobaric surface is sloped? It's sloped that way. That's why the winds are blowing down slope. Up here, this isobaric surface is sloped the other way. That's why the winds are blowing the other way. So that causes this, right? The winds are going in different directions. What do you call the wind changing of winds as you go higher?
Vertical wind shear.
Okay, so there's vertical wind shear. dB dz. So why do I get vertical shear? Basically, in essence, because I have this. Because of temperature gradients. Now, I want to know, no, okay, do you agree that the wind down here is blowing from high to low pressure? It's blowing from high to low pressure. Why? Because there's no what? Right, we neglect the Coriolis force, right? That's what I'm saying. Because this is what size scale is the sea breeze.
Mesoscale?
It's a mesoscale event. So there's no, we don't deal with the Coriolis force. So the air is going from high to low pressure. What would make the wind faster?
A greater pressure gradient.
I'm going to go backwards on this. Faster wind. Greater pressure gradient. What makes the pressure gradient? What's telling me in the picture the pressure gradient? Do you agree? It's the slope of the isobaric surface. But this isobaric surface is sloped. That tells me the wind. Well, this is delta Z over delta X. So what's delta Z over delta X called?
Height gradients?
And that leads to a greater slope of the isobaric surface. But what leads to the greater slope of the isobaric surfaces? Watch this. Do you understand that the vertical distance between the isobaric surfaces changes? Right? From the left side to the right side, it goes like this. Well, isn't that a greater thickness gradient? Right? But what causes the thickness to change as I go from one side to the other?
Differential heating?
Well, just go with the bottom one, right?
A temperature gradient, yeah.
And now, ultimately what caused it in this case? Differential heating. On the Earth, differential heating, because the Earth is a sphere. Anytime you've got differences in heating, you're going to set up a temperature gradient. The greater the temperature gradient, the greater the thickness gradient. The greater the thickness gradient, the greater the slope of the isobaric surfaces. The greater the slope of the isobaric surfaces, the greater the height gradient, the greater the height gradient, the greater the pressure gradient force. The greater the pressure gradient, the faster the winds. We already said this, there's a name for this. What is this called? What's the concept?
Wasn't it thermal wind?
Oh, there's Shannon. It's good to see you. Well, I don't see you, but I'm glad you're here. That's the thermal wind, right? We said something about you at the beginning of class. I called everybody else awesome. I said, Shannon's here, but she's not here right now, so she's not awesome. But now you're half awesome because there's no camera. Do you have the camera? There she is! Yay! We have our full class. Now I can give you all A's. Just kidding. But that's, so Shannon walks in and goes, thermal wind, that's what this is. Does that make sense to you? So in other words, if the water is really cold and the land is really warm, you're going to get faster winds. You're going to get faster circulation. But do you remember in class, we also said that this could be the cold air could be the North Pole, and this is the equator. So in this case, what would the winds be doing with height? So I'm gonna erase a whole bunch of stuff. Okay, so give me a second. I'm gonna erase all this. That was easy. I get rid of all this stuff. Okay. So all of this, even though I'm erasing it, do you understand this all? This is all still true. I haven't really changed much of anything. Right? And I can even get rid of the Messianic mean and the normal human being. A, B, I get rid of all that. There we go. You good? Here's a question for you. What does the jet stream look like? What do you know about the slope of this isobaric surface? What does the slope of the isobaric surface tell me?
Height gradient.
And therefore,
Um,
ultimately it goes, the greater that is, the faster the winds, right? What's happening to the slope of these isobaric surfaces as I go up? Let me redraw one here. Is this what it looks like in the atmosphere? Imagine a set of plates stacked up and you squeeze this one side of them and they fan out on the other side. The bottom plate stays on the table, all the other ones kind of go. What can you tell me about the slope of the plates as I go higher?
the slopes get steeper.
So what does that tell you about the atmosphere?
The higher atmosphere, the higher in the atmosphere you go, the faster the winds become.
Does that make sense to you? By the way, what happens when I get into the stratosphere? What does the temperature start to do?
Starts to decrease.
Right? No, in the stratosphere? What do you know about the temperature? Right, so you get an inversion, right? You start to get warmer temperatures. So do you agree that the tropopause is lower here than it is here? Right, maybe this. So what happens is these isobaric surfaces tend to do what then? They start to reverse like this. When I go in the stratosphere, because now it's warmer than it is over here. So the winds, where are the winds strongest in the atmosphere? At the tropopause. Do you agree the winds are strongest at the tropopause? But what do you know about the slope, which is the wind speed of this isobaric surface? What do you know about the slope at any point on a straight line?
It'll always be the same.
Right? It's always the same. So if the slope anywhere on this line is the same, then the wind would be everywhere the same. But is that what the jet stream is? Isn't the jet stream like a narrow corridor of strong winds? So this is not what the atmosphere looks like if I'm dealing with the equator to the poles. What it really is that, where did it go? What it really is this. And I gotta erase these now. Hold on. It goes more like this. Now, what can you tell me about what's true right here?
There's extremely fast winds.
And that's what the jet stream looks like. It blows into the board because its Coriolis force is affecting it. And you have this strong wind blowing into the board. And so what we get is if it's steeply sloped in this region, I mean, it's kind of sloped over there. If it's steeply sloped in this region, that tells me there is a much stronger temperature gradient from there to there. Remember, a temperature gradient is a change in something, in this case temperature, over a distance. So I might be taking the same temperature change, but instead of being over North Pole to the equator, it's now over a much shorter area, shorter distance. So, well, what do we call when the temperature gradient is really strong from one place, let's say T minus delta T to T plus delta T, where it's warmer? What do you tell me? What do you call a region on the ground of a strong temperature gradient? Ryan?
Sorry, can you say the question again?
What do you call it when there's a strong temperature gradient at the surface? Aaron, are you raising your hand?
Yeah, she says a front.
That's what a front is. That's what a front is. So in other words, when I have strong temperature gradients and I start thinking about fronts, because that's what we call it, that tells me something, that there must be a strong jet above me. Because if there's a strong temperature gradient, there's a strong thickness gradient. And if there's a strong thickness gradient, then these isobaric surfaces are steeply sloped. And isn't that what happens if I go from the equator to the North Pole in the hemisphere? I go from the equator through the tropics, temperature doesn't really get warmer on average or colder by much, maybe a little bit. And then I go to Florida and it's still pretty warm in Florida. And I go up north and I go to Southern Illinois. And then all of a sudden, when I go to Northern Illinois, the temperature drops by 30, 40 degrees. I go past the front. And above me is a strong jet stream. And then the temperatures don't change much as I go to the north. Okay, so let's look at this. Let's look at a model. I'm going to go to the GFS so that I can always find something I want. And this time I'm going to go to North America. And I'm going to look at temperatures. Do you agree at this time there is a pretty significant temperature gradient from there? Look at the temperature. Can you I don't know if you can read that, Kevin.
No.
17.
Wow.
And over here the temperature is 71.
Wow.
That is a big temperature gradient across this small area of Canada. Watch where the jet stream is. Oh, here, I'm gonna even do it this way. I think I can erase this, can't I? There's a strong temperature gradient from there to there. I didn't mean that. I meant that. I've got winds that are strongest right about there. A little bit to the north, and then over here I'm starting seeing it. Actually, I think I want to do this. There. That's where my strongest winds are. Right in here. With that temperature gradient. What about down here? Let's look at the temperature gradient down there. Do you agree that I have temperatures here that are what? 80 something, and then I go up here and there's 40s. That's a pretty strong gradient. There's a front in here. There's a front that goes actually all the way. I would say the front's in here someplace. From the area of low pressure, there's a front. And that's where the jet stream is strong. Actually, do you notice that the front is actually a little bit further south than where the jet stream is? Okay, so the reason for that is this. Let me go to polar front theory. And we'll do some images. What's a good picture of it here? I know it's in black and white, but this is actually pretty good. Do you see that what I'm saying, and maybe you don't, can you read this at all?
Not really.
Is that better?
It's better. Can you read it? No.
Okay, so what I'm saying is I've got a front in here someplace. And what's the warm air doing? The warm air is rising. And what's the cold air doing? Cold air is sinking. And so remember that the cold air is sloped like this. Remember we drew our front the other day? So that the cold air cuts underneath it because it's dense and it spreads out because it's dense air. So what this is saying is that the strongest jet stream is going to be over here someplace. So here's where the front is at the ground. That's its location here. And there's where the jet stream, the polar front jet. And that's what we've got in our scenario. So now when I go back to this, I see that the jet stream I don't know if I can go back. Yep, the jet stream is just north of where the cold air is coming up. Does that make sense to you? Now, if I'm standing here, right there, where this area right there, do you agree that I'm in cold air? But the front is over me. So if I go up, do you agree that I'm going to go from a cold air mass to a warm air mass? Let's see if I can show you that. I'm not going to show you this one. Let me see if I can find a better example of it. Here. Maybe here? I don't know. Got to give me, I'm trying to figure it out. There we go. You see the temperature here is like 54 degrees. The temperature here is actually like 56 degrees. It's warmer the higher up I go. Well, why is that? Because I'm in cold air, it's shallow, and then above me is warm air. Think about the cold front looking like this, right? Cold air underneath warm air. So if I send out a weather balloon, do you agree that the temperature of this balloon would be in the cold air, and then it would be an inversion as they go in the warm air? And that's what I see right there. So that is an inversion because of the front. At least that's the forecast. Does that make sense to you? Give me some feedback. I can't hear you if you don't talk.
That makes sense to me. Yeah.
Yep.
That makes sense.
Okay. So in here, by the way, notice that there's an area of low pressure. There's also an area of low pressure here. Now, in here, I would probably say there's a warm front. Do you see that the temperatures south of the front are in the 60s? And then they go north of the front, the temperatures start to drop off. Do you see the colors getting closer together? So I have a gradient, and there's a little bit of a wind shift. Then I would say there's probably a cold front in this trough where the winds shift direction, something along those lines. So I'd probably put the cold front somewhere around there. And I've got temperatures in the 70s, and then they drop off to the 50s pretty quickly. So I have this cooler air mass and this warmer air mass kind of going into there. By the way, look at these backed winds, southeast winds. That'd be nice, Sam, if you had that over the plains. Anyway, over here, I have a trough into another area of low pressure. And what this typically means to me is that this is really my occluded front. So we have an occlusion is what we've got. This is a new low that forms. Let's see if I can go back and see if it shows you that. Actually, I'll have to go to the US sector to do it. Trying to see if there's a good example. No, this is not a good example. You would think it would be a better look. I mean, this is Monday night. Look how cold it is everywhere. Can you still see me okay? Just my internet. Look, the winds are all out of the northwest or northeast. It's very cold. Look at how cold Colorado is. You know why? You know what's happening in Colorado? By the way, I'm just going to show you something.
Is that the mountains?
It's no, well, some of the mountains, but there's cold air here. It's snowing. So this kind of sucks. Very cold air mass. You remember, did we talk about anomalies in this class? Departure from normal. Look at the average temperature is supposed to be 61.7 and the actual temperature is 33. It's 28 degrees below normal. Every place in blue is like more than 5 degrees colder than normal. So we have this big area of cold air next week. That is just brutal. Look at how much colder than normal. The temperature is 36. It's supposed to be 78 degrees at this time in Colorado. 41 degrees below normal. That sucks. Here, well, we're closer to normal. But still, 65 is normal. It's only 58. When do we get warmer than normal? I mean, really warmer than normal? Maybe the 18th. Oh my God, look at this, would you please? 35 degrees below normal. It's 30. The forecast says it's going to be 36. It should be 71. Crap. That's why there's no thunderstorms. Look at this. This is May 20th. And at Rockford at May 20th at 7 p.m., this forecast says it'll be 41 degrees. It should have been 63 degrees. 22 degrees below normal. Sam, I'm blaming you for this because you're in Wisconsin. You're closer to Canada, so but that's a long way away. I hope it's wrong. Oh my goodness. That's just stupid. Sorry, I'm gonna go look at something. Look at this. Here's your temperatures. The probability of temperatures below normal for 6 to 10 days. That's really cold. Look at it for 8 to 14 days. It's still pretty cold in the east. Like May is going to be a cold month. And then we'll probably go to summer and it'll go 95 degrees out of nothing. No 70s, no low 80s, just immediately middle summer. I hate that. Okay, so I'm kind of digressing, but that's what's going on with the wind. So do you agree that the greater the temperature change, the faster the wind speeds? So whenever I see something like this, if I say, here's the jet stream, do you understand, not only do I know where there's divergence and convergence, but I know north of the jet, it's going to be cold, and south of the jet, it's going to be warm. And an upper level low, which makes this a what? Which way is the air curving here?
Cyclonically.
So that's a trough. Trough, when I have an upper level trough, this is an area of cold air. That's what makes it a trough. And what's a ridge?
Anticyclonically, so it's
Warm
warmer.
air. It's moving anticyclonically. And that's how this works. So again, I go back to the models and you should be able to figure out really easily where there's going to be cold and warm. Right? Here's the jet stream. Cold. Warm. Don't believe me? Here's temperatures. Cold, warm. Polar vortex is a chunk of cold air. That's all it is. Coming out of the Arctic, just dislodges, comes southward. That's what we mean by upper level troughs and low level stuff. But when I look at this, where do I expect surface low pressure? Downwind of an upper level trough, especially if I have a short wave, which I look at here. I'm not going to get into this. I will probably have some low pressure out here someplace. So at the surface, I go, where's the area of low pressure? And there's my area of low pressure, low pressure, low pressure. I get one storm that kind of comes up and it wraps into the cold air, and then it occludes and I get a new low forming. And what happens to this low as time goes on? Gets a little bit stronger, moves up the East Coast. There it is later. That's how weather works. You see, for all of this stuff, there's a combination. It doesn't say. Was I recording it? No, okay, so we're resuming. Let's just talk about one more thing. Actually, it's not talking about one more thing. We already talked about it. Review one more thing. So something to keep in mind, right? Here we have the jet stream. And we said that we have isotherms that do this. Right, this is isotherms. And so we have an area of warm air advection, and we have an area of cold advection. And if we can imagine this, we'll just add to another warm air advection over here. Now, where would the low at the surface form? Well, the low at the surface forms here. And do you agree that we have a warm front and a cold front? And the strongest cold air advection at the surface is there. And the strongest warm air advection at the surface is there. Do you see that as we go north of the warm front, we're going higher in the atmosphere? Warm advection goes up over it. In some meteorological things, it's called a warm conveyor belt. Behind it, we have cold air. And you see that the cold air comes down. This is upper level cold air. This is low level cold air. So everything's sort of sloped in 3 dimensions. You have to kind of picture this. Cold air is coming down, warm air is going up and around. A lot of times when you have a system that's occluded, let's do this. When you have a system that's occluded weather system satellite. When we have an occluded system like this, what shape do you say this cloud is? These clouds are. What's Aaron saying?
I'm lost, just a minute.
Okay, we'll give you a second.
It's a spiral.
Well, think about grammar. This is what we call a comma head. See how we have, I'm sorry, we have a big area of low pressure associated with this. And we have this big comma head storm. So typically what happens is you have a cold front like this. And then the warm front's tucked back here someplace. And then if it's really a big, like if it's really clear, we've got cold, we have an occlusion here. And then we've got, do you remember we said there was a warm conveyor belt? It comes up and goes up like this with the warm advection. Here we have dry air coming in like this. So this is known as the dry intrusion. Because the dry air comes in and sinks. There's, you're not going to need to know this, but there's cold conveyor belt does this actually. But that's neither here nor there. So that's where we get the big comma head storm. When we see that, we know the system's occluding. Okie dokie. Everything's tropical cyclones, which is what they call them in Australia. They have a lot of videos out there. I thought I'd find this quickly. Bureau of Meteorology, what do we call? Vorticity. Let's try this. What was the thing that I Did I show you one of these before? Here, this. I want other. Oh.
Australia's highly variable climate is influenced by the broad patterns in the oceans around it, and the jet streams are another name for fast-flowing currents of air. There are many different jet streams that exist at both high and low levels in the atmosphere. Each has an important role to play in the weather experienced on Earth. The major jet streams that circle the Earth are found just below the tropicals at a height ranging from 9 to 16 kilometers and can reach speeds over 200 miles per hour. They are hundreds of kilometers wide, but only a few kilometers deep, so often described as a ribbon of very strong winds. The major jet streams are the polar front and subtropical jets. These occur in both the northern and southern hemispheres and are part of the larger global circulation. The polar front jet occurs over mid-latitudes and strongly influences the weather over the UK and Europe. The polar front jet is a type of thermal wind that arises due to the strong temperature contrast between cold polar air and warm tropical air. To explain this further, imagine two columns of air, one in the cold air to the north of the jet and one in the warm air to the south. The top of each column is bounded by the tropicals. A shorter column of cold air exerts the same surface pressure as a taller column of warm air. This is because in the cold air column, the air is more dense. This causes atmospheric pressure to decrease more quickly with height. In the warm air column, pressure does not decrease as rapidly with height because the warmer air is less dense. The tropicals in both columns is at the same atmospheric pressure. So if you were to climb to the same height in both columns, you would find that you would be at a lower atmospheric pressure in the cold air column and a higher atmospheric pressure in the warm air column. The pressure difference caused by this temperature gradient produces a pressure gradient force. The pressure gradient force acts from high to low pressure, so theoretically in the northern hemisphere, air would flow from south to north. But the Coriolis force resulting from the Earth's rotation causes the air to move to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. In both hemispheres, the jet stream flows parallel to this temperature gradient, moving from west to east. Theoretically, this jet encircles the Earth in a continuous line, but in reality, it is more broken up, as differential heating of land-sea masses lead to west to east temperature contrasts, as well as north to south. As the polar front jet forms due to the temperature contrast, the stronger the temperature gradient, the stronger the jet. This means that the jet is stronger in the winter than the summer as the poles cool during the winter months, increasing the temperature contrast. In the northern hemisphere, the jet tends to be further south in winter and further north in summer. This is due to the tilt of the Earth, that in the winter, the northern hemisphere is tilted away from the sun, and in the summer, it is tilted towards the sun. Mid-latitude low-pressure systems occur on the polar or northern side of the jet stream, while more settled, warmer conditions are found to the south. This gives us the wet and windy weather we often see in the UK during the winter months, as low-pressure systems are steered towards us. It can also lead to some disappointingly wet summers if the jet stream remains to the south of the UK. A stationary jet stream pattern will bring frequent low-pressure systems to the same region. When warm air moves further north than normal, or cold polar air moves further south, this can change the prevailing west to east jet stream pattern. This causes the jet stream to buckle, driving depressions towards different regions or blocking their movements altogether. A straight west-east flowing jet stream won't have much impact on the development of new weather systems or
That's
strengthening
zonal.
pre-existing ones. When a jet stream meanders north and
It's
south,
meridianal.
air accelerates and decelerates around the bends in the flow. These areas of changing speeds are our development areas. Where the air is accelerating, more air is leaving than entering a certain point. This means that the air is being depleted at this point. To fill this depletion, air from below rises. When air rises, it forms clouds and precipitation. Winds at the surface converge to this rising air column, which causes surface pressure to fall, and a low pressure system may develop or deepen further. So whilst the jet stream is just an area of fast flowing air, it has a fundamental effect on our weather.
All right, level of understanding on that one. That's kind of cool to watch that video and go, yeah, I kind of understood what's going on with that. How you doing, Aaron? Where are you at?
Said 5.
5? Zach, what did you say?
I said like 4.
Okay, so that's just kind of a fun thing. Let's do this. Let's go to, am I still sharing the screen? Yeah. Let's go to Unit 4 notes. Because now we're looking at what we're going to be being tested on. We have all this stuff. I think everything here we've gone through. 2 omega v sine phi, friction, development of, let me see, curve low with friction, hydrostatic, air masses, we've talked about that, fronts and cyclones. These are all extratropical, outside of the tropics. Cold fronts are usually steeper. Warm fronts are a little bit more gradual. Front speed, occluded fronts overtakes the warm front. Now there's 2 types of occlusions. I'm not going to worry about them. Just you have to figure out, if you recall on an occluded front, when you have low pressure and you have a warm front here and a cold front there, right? And then here's the occluded front. So this is where there's cold air. This is where there's warm air, the warm sector. But the question is, what is the air here compared to there? Do you read it's cold? But if this air is colder than this, then this air is going to continue to be forced up. If this air at the circle is colder, then this air is going to act like a warm type of occlusion, like a warm front on top. That you can think about that. I'm not too worried about it. Frontogenesis is the beginning of a front. So by increasing the temperature gradient, that's making the front stronger. Decreasing, it's called frontolysis. If you develop a cyclone, that's cyclogenesis. Obviously, if the cyclone goes away, it's cyclolysis, but you don't hear that word very often. We have already talked about the occluded stage. And then we go into thunderstorms. So thunderstorms, we talked about what are the ingredients we need? Lift, moisture, instability. The thing is, if we want a thunderstorm that's severe, we need to get the winds aloft to be at a different speed or direction than the winds here. So severe weather means I've got vertical wind shear. Okay, and the more vertical wind shear gets us from a single cell to these other types of thunderstorms. So this is increasing. Now, you should know what severe is. Did you already do that worksheet? What worksheet is left?
None.
Isn't there one more sheet that you have to do this week?
I think we've done them all.
Oh. Well, what does severe mean? What does it mean to be severe? Three things could be possible.
It was hail over an inch. Winds over, what was it, 60 miles per hour? And then lightning.
Okay, no, not lightning. Definitely not lightning. So hail, 1 inch, well, or more in diameter. So that's the size of a quarter, a coin. Damaging winds. How fast are those winds, Sam?
Must be at least 50 knots or 58 miles per hour greater.
58 miles an hour, good. And then what's the third thing? Not lightning. Lightning and rain don't make it severe. What's the last thing that makes a storm severe?
Tornado.
Tornadoes. Okay. So we're going to go through this. So what I want you to do is just kind of look at this, and then we're going to talk about hurricanes. So those are the two things left. Thunderstorms and hurricanes. We have a whole week to do this. I've never been this far ahead. That's because we didn't do a lot of conversations that we normally do in class. So that's it. We'll do that next week.